In the early 2000s, to drive a Toyota Prius was to make a statement. It was more than a car. It was a cultural artifact, a rolling symbol of environmental consciousness and forward thinking. From the driveways of suburban families to the garages of Hollywood's elite, the distinctive aerodynamic silhouette of the Prius became the emblem of a greener future. Toyota wasn't just participating in the conversation about the future of the automobile. It had started it. The launch of the first-generation Prius in 1997 was a shot heard around the world. The first mass-produced hybrid vehicle, a technological marvel that seamlessly blended a gasoline engine with an electric motor. For 2 decades, Toyota reigned as the undisputed visionary of electrification. While other automotive giants were still perfecting the internal combustion engine, Toyota was building a new empire. The company sold over 18 million hybrids, creating a legacy of unmatched fuel efficiency and legendary reliability that became the bedrock of its global dominance. They had seen the future a decade before anyone else, and for a time, it seemed they owned it. The Prius wasn't just a car, it was a promise from the world's largest automaker that it would lead the way into the 21st century. This is the story of what happened when that promise appeared to be broken, and the monumental multi-billion-dollar gamble the company is now making to keep it. Step into the electric vehicle market of today, and you will find a ghost. Where one would expect to see the pioneer of electrification standing tall, there is a conspicuous void. The world's largest automaker, the company that taught the world the word hybrid, is a near-invisible player in the all-electric revolution. The numbers are not just unflattering, they are staggering in their insignificance. In the first quarter of 2024, as the global market for battery electric vehicles, BEVs, surged, Toyota sold a mere 1,897 units of its flagship EV, the bZ4X, in the United States. This accounted for a minuscule 0.4% of the company's total sales in the same period. This wasn't a strategic retreat, it was a rout. While competitors like Tesla, Hyundai, and Kia were selling EVs by the hundreds of thousands and capturing significant market share, Toyota was struggling to clear 1% of its own output. The launch of the bZ4X, meant to be Toyota's grand entry into the modern EV era, was a case study in corporate miscalculation. It arrived late, with a limited production run, and was almost immediately hobbled by an alarming safety recall that saw wheels literally falling off the vehicle. Reviews were mixed at best, and the market reacted with a collective shrug. The failure was so profound that Toyota itself was forced to publicly confront it. The company drastically slashed its own global EV sales forecast, cutting its target from 202,000 vehicles down to just 123,000, a nearly 40% admission of defeat before the race had even truly begun. While its rivals were boasting EV sales shares in the double digits, Toyota was a giant left, gagging on their electric dust. The central question became unavoidable. How did the undisputed leader of the last automotive revolution fall so catastrophically behind in the new one? Toyota's failure to launch in the BEV space was not an accident, nor was it born of ignorance. It was the direct result of a methodical, deeply entrenched corporate philosophy, championed for years by Akio Toyoda, the company's former CEO, chairman, and heir to the founding family dynasty. Toyota was a vocal skeptic of an all-electric future, consistently arguing for a multi-pathway approach that heavily favored the hybrid technology his company had perfected. In his view, and by extension, in Toyota's official corporate stance, the world was not ready for a full EV transition. The infrastructure wasn't there, the battery technology was immature, and customers, he argued, still wanted choice. This philosophy was not just a talking point, it was a fortress built to defend a phenomenally successful business model. In the years that competitors were pouring billions into BEV development, Toyota was enjoying unprecedented demand for its existing lineup. Waitlists for wildly profitable trucks and SUVs like the Tacoma and 4Runner stretched for months. From a purely financial perspective, there was no urgent incentive to pivot to the high-risk, lower-margin world of BEVs. Why gamble on an uncertain future when the present was so lucrative? This internal logic was reinforced by a powerful external campaign. Toyota became one of the most active lobbyists against aggressive EV mandates, working in Washington and other global capitals to slow the transition and shape regulations to favor its hybrid-heavy fleet. The company's immense success with the Prius, its greatest triumph, had calcified into a corporate dogma. The belief that hybrids were the most rational, practical path to decarbonization became an unshakable truth within the company's walls. This worldview led them to fundamentally misread the market's tectonic shift, a shift driven not by pure consumer demand, but by the disruptive force of Tesla and the powerful pull of government incentives. They saw pure BEVs as a niche, a compliance play for states with strict regulations, rather than the inevitable successor technology. Their greatest strength had become their greatest weakness. The very innovation that had put them a decade ahead of the curve had created the cultural and financial inertia that now left them a decade behind. To understand the depth of Toyota's wager, one must first understand the enemy it seeks to vanquish. The modern electric vehicle is built around a silent, powerful, and deeply flawed heart: the lithium-ion battery. For all its revolutionary potential, the conventional battery that powers every Tesla, every Hyundai Ioniq 5, every Ford Mustang Mach-E, is a system of elegantly managed compromises, where every component designed to enhance performance simultaneously introduces a new and significant risk. At its core, a lithium-ion battery is a simple device composed of four key parts: a positive electrode, the cathode; a negative electrode, the anode; a porous separator to keep them from touching; and a crucial liquid electrolyte that allows lithium ions to flow between them. It is this last component, the electrolyte, that represents the technology's original sin. In nearly all high-performance lithium-ion batteries, this electrolyte is a highly flammable organic solvent. It is, in essence, a chemical cousin to gasoline, a volatile liquid energy carrier sealed inside a metal box. This single fact is the source of the battery's greatest danger, a phenomenon known as thermal runaway. Thermal runaway is a chemical chain reaction, a domino effect of self-sustaining heat that, once triggered, is nearly impossible to stop. It can be initiated by a number of faults: a manufacturing defect, physical damage from a crash, or most commonly, overcharging or internal short-circuiting. The process unfolds in a terrifying, predictable sequence. It begins around 80 degrees Celsius, 176 degrees Fahrenheit, when the protective layer on the anode, known as the solid electrolyte interphase, SEI, begins to break down. This exposes the highly reactive electrode materials to the electrolyte, initiating further heat-releasing reactions. As the temperature climbs past 100 degrees Celsius, 212 degrees Fahrenheit, the liquid electrolyte itself begins to decompose, releasing a cocktail of flammable hydrocarbon gases like methane and ethylene. This is what causes a battery to swell and vent smoke before a fire begins. The point of no return often comes around 130 degrees Celsius, 266 degrees Fahrenheit, when the thin polymer separator melts. This allows the cathode and anode to make direct contact, causing a massive internal short circuit that unleashes the cell's remaining energy as a torrent of heat. The temperature can skyrocket past 600 degrees Celsius, 1112 degrees Fahrenheit, in milliseconds. In the final catastrophic stage, the cathode material itself, typically a metal oxide, breaks down and releases oxygen atoms. This is the ultimate nightmare scenario. The fire now has its own internal oxygen supply, allowing it to burn hotter and making it incredibly difficult to extinguish with conventional methods. It is a chemical fire that brings its own fuel and its own oxygen, sealed inside a box. This fundamental safety problem is what solid-state batteries and Toyota's strategy promise to solve once and for all. Beyond the ever-present risk of fire, the design of the conventional lithium-ion cell imposes fundamental limits on performance, creating two problems that have defined the EV experience for a decade: range anxiety and charging time. The first problem is the graphite ceiling. For decades, graphite has been the universal choice for the anode material in lithium-ion batteries. It is abundant, cheap, and structurally stable. During charging, lithium ions nestle between its carbon layers in a process called intercalation. But this stability comes at a cost. Graphite has a limited theoretical capacity of just 372 mAh per gram, mAh per gram. This acts as a hard ceiling on the battery's energy density, the amount of energy it can store for a given weight or size. To give a car more range, manufacturers have only one option: add more battery cells, making the pack bigger, heavier, and more expensive. This compromise is the very source of range anxiety. The second, more dangerous problem is the dendrite menace. This issue arises from the desire for fast charging. Pushing a high electrical current into the battery can overwhelm the graphite anode. Instead of neatly intercalating, the lithium ions begin to pile up on the anode's surface, plating it with pure metallic lithium. This metallic buildup doesn't grow smoothly. It forms sharp, needle-like structures called dendrites. These dendrites grow through the liquid electrolyte like metallic trees, and if they grow long enough to pierce the fragile separator and touch the cathode, they create a direct internal short circuit, the very trigger that can initiate catastrophic thermal runaway. This reveals the central paradox of the lithium-ion battery. The liquid electrolyte enables performance, but creates a fire risk. The separator prevents short circuits, but is vulnerable to dendrites. The graphite anode manages dendrites but limits range. Every component is a compromise, a delicate balance between performance and peril. It is a technological paradigm that has reached its limits, a tyranny that can only be overthrown by a revolution in chemistry. For decades, the solution to the tyranny of the liquid cell has existed as a theoretical ideal, a near-mythical technology whispered about in research labs and academic papers. It has been called the holy grail of energy storage, the solid-state battery. This is the technology that Toyota has wagered its future on, a revolutionary leap that promises to solve not just some, but all of the fundamental problems of the lithium-ion age. The core innovation of the solid-state battery, SSB, is as elegant as it is profound. It replaces the flammable liquid electrolyte and the flimsy polymer separator with a single solid component. This solid electrolyte is a marvel of materials science, a solid material, often a ceramic or a polymer, that is engineered to be an exceptional conductor of ions, but a perfect insulator of electrons. Researchers are exploring three main families of solid electrolytes. Polymer-based electrolytes are flexible and easier to manufacture, but suffer from low conductivity at room temperature. Oxide-based electrolytes are highly stable, but brittle and difficult to process. The third category, and the one that has captured the focus of Toyota and many others, is sulfide-based electrolytes. These materials, like lithium phosphorus sulfide, offer a tantalizing combination of properties. They are soft and deformable like polymers, but possess ionic conductivity at room temperature that is on par with, or even exceeds, that of traditional liquid electrolytes. By eliminating the flammable liquid, the primary cause of thermal runaway is engineered out of the system from the start. The true genius of the solid-state battery, however, is not just what it removes, but what it enables. The mechanical stability and chemical inertness of the solid electrolyte unlocks the ultimate prize in battery chemistry: the use of a pure lithium metal anode. This is the anode material that scientists have dreamed of using for half a century. Lithium is the lightest metal on the periodic table and has the highest theoretical energy storage capacity of any potential anode material, over 10 times that of graphite. In a conventional battery, using a lithium metal anode is impossible. The liquid electrolyte reacts violently with it, and the dendrite growth during charging is uncontrollable, leading to rapid short circuits and fires. But a well-designed solid electrolyte acts as an impenetrable physical barrier, suppressing dendrite growth and allowing the battery to safely harness the immense energy potential of pure lithium. This single change fundamentally rewrites the rules of battery design. By replacing the bulky, low-capacity graphite anode with a thin, hyperdense layer of lithium metal, the energy density of the battery can be dramatically increased. This means an EV could have twice the range with a battery of the same size and weight, or the same range with a battery that is significantly smaller, lighter, and ultimately cheaper to produce. This technological leap translates into performance claims so extraordinary they seem to belong to science fiction. They represent not an incremental improvement, but a complete paradigm shift in what is possible for an electric vehicle. First, range. The graphite ceiling is shattered. Toyota is targeting an initial range of 745 miles, 1,200 kilometers, for its first-generation solid-state batteries, with a clear roadmap to a future version capable of over 932 miles, 1,500 kilometers, on a single charge. This isn't just an improvement, it's the eradication of range anxiety. A car with this capability would travel farther than almost any gasoline-powered vehicle on the road today. Second, charging. The dendrite menace is tamed. Without the risk of lithium plating on a graphite anode, charging can be done at incredible speeds. Toyota's target is a 10-minute charge time to go from a 10% to an 80% state of charge. This transforms the EV ownership experience, making a long-distance road trip stop as quick as a visit to a gas station. Third, safety. The risk of fire is virtually eliminated. The solid electrolyte is non-flammable, and the entire structure is more stable at high temperatures, making thermal runaway an exceedingly unlikely event. Finally, lifespan. The solid structure is more durable and less prone to the chemical degradation that plagues liquid cells. The result is a battery that could last for 15 to 20 years, or well over 500,000 miles, potentially outlasting the vehicle it powers. The scale of this promised revolution is best understood through direct comparison. The solid-state dream is not about making a better battery, it's about creating an entirely new category of energy storage. For years, the narrative has been set. Toyota, the cautious giant, the EV skeptic, the laggard that missed the boat. But while the world was watching its empty electric showrooms, a very different story was unfolding in the quiet, secure confines of its research labs and patent offices. The company's public hesitation was not a failure of vision. It was a strategic deception, a corporate rope-a-dope designed to mask one of the most ambitious, long-running, and secretive R&D campaigns in automotive history. While its rivals fought a bloody war for the present, Toyota was quietly waging a war for the future. The most stark evidence of this secret war lies in the global patent database. An analysis of intellectual property related to solid-state batteries reveals a stunning reality. Toyota is not just a player, it is the undisputed titan. The company holds over 1,331 granted patents specifically for solid-state battery technology, more than double its nearest competitor, Panasonic, and vastly more than the rest of the automotive and battery industries combined. By some counts, including patents filed and pending, the number exceeds 8,000. This is not a random collection of ideas. The patents form a comprehensive intellectual property fortress, covering everything from the fundamental chemistry of novel electrolyte materials to the intricate structure of the battery cells themselves. Most importantly, a significant portion of this portfolio is dedicated to something far less glamorous, but infinitely more critical: manufacturing processes. This reveals a strategy aimed not merely at invention, but at industrialization. Toyota has not just been trying to design a better battery, it has been systematically building a legal and technical moat around the ability to mass produce it. This patent dominance suggests a long-term plan to control the means of production, potentially forcing competitors into costly licensing agreements or locking them out of key technologies altogether. Toyota's quest for a better battery did not begin in response to Tesla. Its roots run far deeper, back to the very origins of the company. In 1939, just 2 years after the Toyota Motor Corporation was formally established, it founded a dedicated battery research laboratory. This was a direct fulfillment of the final wishes of Sakichi Toyoda, the company's patriarch and a legendary inventor, who believed that mastering energy storage was fundamental to the future of industry. This century-long institutional focus on foundational energy technology provides the crucial context for their current strategy. The 2 decades and billions of dollars spent perfecting the hybrid powertrain for the Prius were not a detour from the path to pure electrics. They were the training ground. It was during this period that Toyota built up an unparalleled expertise in battery chemistry, power electronics, and systems integration. Their modern push into solid-state technology began in earnest far earlier than most realize. The company initiated its formal solid-state research program in 2010. By 2020, while the world was still fixated on its lack of a competitive BEV, Toyota was already conducting road tests with a running prototype vehicle powered by its own solid-state battery, a fact it quietly revealed in a corporate news release. This was not the action of a company scrambling to catch up. This was the action of a silent giant patiently executing a multi-decade plan. The company has poured staggering sums into this effort, with a stated investment of over 11.6 billion euros, approximately $13.5 billion, earmarked for battery R&D through 2030, a significant portion of which is dedicated to bringing solid-state technology to market. An invention in a lab is worthless without a path to the factory floor. Toyota, a master of mass production, understands this better than anyone. Recognizing the immense challenge of commercializing a completely new battery chemistry, it has spent the last several years forging a series of critical strategic alliances designed to solve the 2 biggest hurdles: manufacturing scale and supply chain security. The first pillar of this strategy is its deepened partnership with Panasonic. In 2020, the 2 Japanese giants formed a joint venture called Prime Planet Energy and Solutions. This venture combines Toyota's deep knowledge of battery chemistry and vehicle integration with Panasonic's decades of experience as a high-volume battery cell manufacturer. Its explicit purpose is to develop the processes and infrastructure needed to mass-produce Toyota's next-generation batteries, including solid-state cells. This is the alliance for scale. The second, and perhaps more crucial pillar, is the partnership with Idemitsu Kosan, a Japanese petrochemical giant. The most promising solid electrolytes are sulfide-based, but producing these materials at automotive scale is a massive chemical engineering challenge. Through this alliance, Idemitsu is leveraging its expertise in large-scale chemical production to become Toyota's dedicated supplier. Idemitsu is now building a large pilot facility with plans for a full-scale plant, specifically to produce the raw lithium sulfide electrolyte that will form the heart of Toyota's solid-state batteries. This is the alliance for securing the supply chain of the single most critical and novel component. Taken together, this strategy reveals a company that has been playing a different game all along. While competitors focused on the first generation of EVs, Toyota was quietly building the arsenal needed to win the second. They absorbed the criticism, endured the poor press, and allowed the world to believe they were a laggard, all while executing a deliberate long-term plan to bypass the current technological paradigm and emerge as the dominant force in the next.